Let's take a look at the idea of proving trigonometric identities. An equation that is true for every variable is called an identity. And here are two possible candidates. One of them turns out to be an identity and the other one's not. So let's take a look at how we can tell when something isn't an identity and what we have to do to prove that something is an identity. To show that something isn't a trigonometric identity, we need a counterexample. This upper equation turns out to not be a trigonometric identity, and we can see a counterexample by using the calculator. If I enter those two expressions, if I enter the right-hand side and the left-hand side into the calculator as y1 and y2, I get sine of 4x for y1 and 4 times sine of x for y2. And then I could either go to the graph and I would very quickly see that these are two different expressions, or I could go to the table, and because an identity has to be true for every angle, if I enter any number into this expression, what comes out should be the same. And for a value like 1, we happen to be, I think we're in degree mode here, and so the value 1 represents 1 degree, and the values are pretty close, but they aren't quite exactly the same. A clearer example would come from 30 degrees. At 30 degrees we see that the first expression is equal to 0.866 and the second expression is equal to 2. So this expression is not true when x equals 30 degrees, which means that it's not an identity. In a similar way, we could check the second expression to get a sense of whether we should consider it an identity or not. And so we still have the same sine of 4x. The second side of the expression is 4 times sine of x times cosine of x cubed, using the caret key to introduce a cube, and then minus 4 times sine of x, closing the parenthesis, adding a cube, times cosine of x. And now if we go over to the table, I see that at 30 degrees they are exactly the same. And I can really type in any other value and I'll see the same thing at 32, at 45, at negative 27. The values are the same on both sides. Unfortunately, that doesn't prove that the identity is an identity, because we tested the expressions at 5 different values, which is a pretty good start, I guess, but there are an infinite number of angle measures that we could plug into this formula, and we want it to be true for all of them. So what we need, rather than just having a numerical justification at a few different points, we'd like to have an algebraic justification that shows that for any particular angle, the left-hand side is always going to equal the right-hand side. To do that, we want to set up a proof that provides a step-by-step manipulation of one side to turn it into the other. Or for some identities, we can prove, one side we can get it to a certain expression and then move the other side to get it to a certain expression. But both of those, they create a connection of sort of simplifications that we can understand at each step that take us from one side to the other. So let's walk through what this could look like. And there are different ways to do this. Let me start with the left-hand side. And one thing we could do, again, it's not the only thing that we could do, but I could think of that 4x as 2 times 2x. And then I could use the double angle identity, but instead of just having an x inside, I could have 2x. So let me set this up. So I know that sine of 2 theta equals 2 times sine of theta times cosine of theta. Within this expression, I can consider that theta to be 2x. Because what I have here is 2x, right? So that's my theta in this expression, which means that using this identity, I can rewrite sine of 2 times 2x to be 2 times sine of 2x times cosine of 2x. So I'm using that identity, the framework of that identity, to rewrite the expression. Of course, we know some identities for the double angle identity. I can use this again to replace sine of 2x with something simpler in terms of just x. And I'm going to use the cosine double angle identity for cosine that says that cosine of 2x is cosine squared theta minus sine squared theta. And so from this first expression, this becomes 2 times 2 sine of x times cosine of x, using the double angle identity for sine to replace that sine of 2x, times cosine squared x minus sine squared x, using the double angle identity for cosine to replace that cosine expression. Right, so each of these steps so far has been, I hope, pretty clear, that we can make the jump from one to the next using the identity rules that we know. Well, I can simplify this a little bit more, and it turns out that we will see the right-hand side in just a moment. So first, let me mention that this is just a bunch of stuff multiplied together. These are just 4 factors. And so to combine them, I can do 2 times 2 to get 4, and then that 2 times 2, that 4 is multiplied by sine of x and cosine of x. Right, so that just simplifies that first part. That is still all multiplied by cosine squared x minus sine squared x. And now, taking those 3 factors, I can distribute them, and I should distribute them across the subtraction. So all 3 of those get multiplied with cosine squared and with sine squared. And so I can think of this as 4 times sine of x times cosine of x times cosine squared of x minus 4 times sine of x times cosine of x times sine squared of x. And now within this group, within this first group of factors, the cosine matches up, so I can add their exponents. And I get 4 sine of x times cosine cubed of x minus 4 sine cubed of x times cosine of x, because in a similar way the sine of x and the sine squared become sine cubed. And so we've proven the identity because step by step, using correct algebraic manipulations, we turned the left-hand side into the right-hand side. And so that's one of the methods that we can use to prove an identity. So let me end the video with the following question. Take a few minutes and try to prove the identity that sine of theta plus cosine theta squared equals 1 plus sine of 2 theta. I hope you enjoyed the video. Thanks for watching.